You've heard the term machine learning thrown around a lot, right? But what does it actually mean for a machine to learn? How is that even possible? Well, today we're going on a tour of the machine learning landscape to really get our heads around how computers go from just following orders to actually, learning.
So that's the big question, isn't it? How do you teach something that doesn't think? Well, it's not magic. It's really more like a recipe. You need the right ingredients, which is the data, that's its experience, and you need a really clear system of feedback to guide it along the way. All right, here's our game plan. First, we'll look at the main teaching styles for machines. Then we'll see how they actually study the material. We're also going to cover what happens when that whole learning process just goes completely off the rails. And finally, how we find that perfect sweet spot for success.
So, just like us, machines have different ways of learning. It really all depends on what kind of teacher they have. And there are three main approaches that pretty much cover everything.
Okay, let's start with two big, kind of opposite ideas. First, you've got supervised learning. The easiest way to think about this is like giving a student a textbook and the answer key. It learns by looking at a problem and the correct answer, which we call a label. Now, on the flip side, you have unsupervised learning. This is like handing the student just the textbook and saying, figure it out. There's no answer key. The whole point is for the machine to find hidden patterns all on its own.
You see a perfect example of this every single day with your email's spam filter. How does it know what spam is? Well, it learned because people trained it on millions of emails that were already labeled spam or not spam. Those labels were its teacher, showing it exactly what to look for. But what if there isn't an answer key? What if the machine has to learn just by doing things, by trial and error? Well, that brings us to the third style, reinforcement learning, which our source material calls a completely different beast. This visual just nails it. Think of the agent, our little robot here, like a puppy you're training. It explores the world, it tries stuff, and it gets feedback. Do something good, you get a treat. That's a reward. Do something bad, you get a no. That's a penalty. After millions of tries, it starts to build a strategy, a policy for getting the most rewards possible. So this becomes a constant learning loop, right? The agent looks around, makes a choice based on its current strategy, and does something. Then it gets that feedback, the reward or penalty. And here's the most important part. It uses that feedback to tweak its strategy. And it just does this over and over and over, getting a tiny bit smarter each time until it finally figures out the best way to do its job. So we've covered how machines learn. Now let's talk about when they learn. Are we talking about a student who crams for the test the night before, or one who studies a little bit every single day? It's a really crucial difference. And that's basically the difference between batch and online learning. Batch learning is the crammer. It takes the entire data set and studies it all in one go. But if you get new information, it's a huge pain. You have to retrain the whole thing from scratch. Online learning, though, that's our continuous learner. It takes in new data in little bits, we call them mini batches, and it adapts on the fly. It's always updating what it knows without having to start all over. So when is this continuous approach a total game changer? Well, it's essential for anything that's constantly changing, like stock market data. It's also great if you don't have a ton of computing power, because you don't have to load a gigantic data set into memory all at once. And for data sets that are so massive they literally can't fit on one computer, this is pretty much the only way you can do it. Of course, just like any student, the learning process can hit some major roadblocks. So what happens when a machine learns the wrong thing or just doesn't learn at all? Let's get into the main challenges. Most problems really boil down to one of two main culprits. It's either the study material itself is bad, that's bad data, or the student just isn't right for the test. That's a bad algorithm. You either have junk ingredients or you're using the wrong recipe. And when it comes to the data, there's one golden rule that everybody in this field lives by. It's simple. Garbage in, garbage out. If the information you feed your model is garbage, the results that come out the other side are going to be garbage too. There's just no way around it. This classic XKCD comic just says it all, doesn't it? This is your machine learning system. Yep, you pour the data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Just stir the pile until they start looking right. You can't just stir the pile and hope for the best. If your data is flawed, you're gonna get flawed results. Period. Now for the bad algorithm side of things. The biggest, most common trap
is something called overfitting. This is the student who doesn't learn the concepts for the test. They just memorize the exact questions on the practice exam. Sure, they'll get 100% on that practice test, but they're going to completely bomb the final because they can't handle any new questions. The model has memorized the training data, including all the random noise, and it can't generalize. The book gives this perfect human analogy for overfitting. It says, imagine you go to a foreign country and the first taxi driver you meet rips you off. You might be tempted to say, wow, all taxi drivers in this country are thieves. You've made a huge, sweeping conclusion from one single bad data point. That is exactly what an overfitting model does. And then you've got the total opposite problem, underfitting. This is when your model is just too simple. It can't even grasp the basic patterns in the data you're giving it. So it does poorly on the practice test, and it does poorly on the final exam. It fails to learn. Full stop. So how do you diagnose which problem you have? Well, this little table is your cheat sheet. If your model gets a really low error on the training data, it aces the practice test, but has a high error on new data, it bombs the final, that's a classic case of overfitting. If it has a high error on both, well, then it's underfitting. It never learned the material in the first place. So all of this brings us to the final and maybe the most critical part of the whole process, the balancing act. The real goal of machine learning is to find that Goldilocks zone, a model that's not too simple, not too complex, but just right. Because at the end of the day, here's what it all comes down to. It doesn't matter how well a model does on its training data. The only thing that truly counts is its ability to generalize. How well does it perform out in the wild, on new data it's never ever seen before? That is the ultimate test of learning. And that really is the art and science of it all. It's about finding that perfect sweet spot. A model that's smart enough to find the real patterns in the data, but not so complex that it starts memorizing all the random noise. It's this constant tug-of-war between underfitting on one side and overfitting on the other. Which leaves us with one final, kind of deep question to think about. Is it enough for a machine to just be right, or does it also need to understand? And that right there is the fundamental challenge at the very heart of building truly intelligent systems.